problem solving assessment is the work that I did when I went back to graduate school after I had been teaching for 7 years. I decided I wanted to actually get a PhD. And so when I went back, this is the work that I did. And it was motivated by trying to understand why my students had trouble and why I wasn't able to help them with their problem-solving problems. I could help them with their content, but I had a hard time helping them become better problem solvers. So I did this work with Carl Wyman, who's now at Stanford University. And so Carl was my advisor when I was at CU, so the two of us together did this work. And right now we're writing up a paper that should be in the American Journal of Physics, hopefully by the spring. So problem solving is arguably the most important skill that a physicist can have. If you ask physics teachers, if you ask students or alumni or other departments, why do students take physics? Because you want them to have better problem solving skills. And since most of you are physicists, you know this. You know that there are a lot of skills that you learn by becoming a physicist and being a physics teacher. So in spite of extensive research, very little progress has been made in understanding how to do a better job of teaching our students to be problem solvers. And we don't have a good way to measure it either. So other aspects of physics learning, we've really made a lot of progress on. Conceptual understanding, for example, the force concept inventory. There's all kinds of resources for different sorts of content knowledge that we're trying to teach our students, but we don't have a way to measure problem solving, and we don't have good research-based effective practices for teaching it. So what makes a good problem solver? So that's what we want to try to figure out. So I'm going to start, there's several definitions of problem solving floating around out there. You might think of students solving back of the chapter problems, or you might think of a graduate student in lab and what they have to go through there. So what do we mean by problem solving? So I stole this definition from Richard Mayer. He's a psychologist at the University of California, Los Angeles, UCLA. And he says problem solving is cognitive processing, so thinking, directed at achieving a goal when no solution method is obvious to the problem solver. So something that might be in the back of an introductory textbook would not be a problem to you all. You would generally know the approach you need to apply and the equations you would want to use, and you would do some analysis to figure out what's going on, and then you would apply those equations and you would work through it. You know what you would need to do, so that means it's not a problem for you. But your students, on the other hand, my goodness, it might take them a couple hours to solve that one problem because they really just don't know what to do. There's all sorts of reasons why they have trouble. So this definition is based on the solver. That's very important that we know that up front for anything that we're going to talk about the rest of the day. So our hypothesis was that the difference between the complexity of the subject and the simplicity of the measurement tools is the problem. Because people are always trying to measure problem solving as one thing. The ACT says they have a way to measure problem solving for college students. They don't call it ACT, but and ETS also says they have a way to measure problem solving. And there's the college learning assessment that universities pay big bucks to have them come in and measure the supposed problem solving skills of their students, and they come back with one number. And that's sort of like you having one number to say how strong of a physics student one of your physics majors is. I mean, problem solving is huge. How can you measure that with one number? So usually all you do is measure whether they can solve a problem or not. And this provides no insight as to what the learner needs to improve, and no guidance to the teacher as to how to help them improve. So how can we get more detail? How can we do something that helps you know what's going on with your students? So we decided we needed to figure out what all those individual skills are. We set out to figure out what you need to do to solve a problem. And we call them subskills. So we set out to measure the subskills. That seems simple enough, right? We need to figure out what they are, and we're going to measure them. Well, physics kind of gets in the way. Because what if somebody is a superb problem solver, but they haven't taken physics before? Maybe they don't know about single slit diffraction. Maybe they don't know about Newton's first, second, and third laws, but they're an excellent problem solver. How would you measure that? If you gave them a problem with Newton's laws and they don't know Newton's laws, they're going to fail. So that says they are no good, but maybe they're not. Or maybe you've got a student who's taken your class and they learned a particular algorithm that they could use. Maybe they learned how if you have a bucket hanging from a string, that tension minus weight equals MA. They may not have any idea how to draw a free body diagram. They may not have any idea how to apply the sum of forces. But they know tension minus weight equals MA. And it looks like they did a really good job. So physics gets in the way. So what do we do about that? Normally, in a research area, you would study experts. And you say, well, let's see what the experts do. If we can figure out what the experts do, then we can figure out what it is a person needs to be able to do. So there's been tons of research on what experts do. And they came up with what you see in all of your textbooks. Okay, draw a picture, describe the physics principles, identify the equation, do your math, and check your answer. So there you go. So does that help you teach your students to be better problem solvers? They get better at bookkeeping, which does help. It does help, but it turns out if you go back to the definition of problem solving, if you're actually problem solving, if I gave Kevin a problem in a related, maybe it's going to be in nuclear physics because you're an astronomer. So maybe I gave you a nuclear physics problem. You don't have that background knowledge. You're not going to do those things. So it turns out that it only looks like that if you're not actually solving a problem. It looks like that if you're solving an exercise. If you're solving something that you're familiar with, where you're already familiar with the solution method. And here, to do a problem, no solution method has to be obvious to you. So right there, that means that research on expert problem solving from the 80s and up to now isn't helping us understand what you do when you really are having a problem. So it turns out that there are several people who have studied experts doing legitimate problems for them. So Schoenfeld has done a lot of research in math, and in '92, and this is actually a while ago, but people don't know what to do with it. He studied math professors solving in a content area that was unfamiliar to him. So that'd be like Kevin trying to solve something in nuclear physics, for example. And so he compared them to what a student does when they solve a problem in that area, and he found out there were definitely differences. These math professors definitely had skills that the students didn't have, and that's what you would expect, right? Weinberg did this in history. What's history have to do with physics? But he found the exact same results that we're finding in physics that we're finding in math. And Chandralekha Singh studied it in physics in 2005, and she gave problems, a very difficult intro level, but very difficult and unfamiliar problems to physics professors, so that they had to really think about it in a new way that they hadn't thought of before. And she found that they also had much stronger skills than the students. And so some of the things that they saw were that the experts were better at visualizing the problem, monitoring their own progress, thinking about, why am I doing this and where is it getting me? Connecting the steps and pieces. Estimation, they need to estimate if something was reasonable or not. And their content knowledge, of course, was far superior. And even though Chandralekha was looking at a physics professor or the problem they hadn't solved before, they still had superb content knowledge in physics that they could apply. The math professor, it may have been a content area that was unfamiliar to him. I'm going to keep picking on Kevin. He has skills that, even though he's an astronomer, that will help him, content skills that will help him in nuclear physics. So anyway, so you'll notice that as I talk about problems throughout this, any time I have it in this font and in the red, those are specific skills that I actually identified through my research also. So if you see them in that font, that's a clue that those are part of what we saw, because there's 44 of them and we're not going to just sit and read them all. So they'll appear intermittently. So we want to figure out, how are we going to measure these subskills? There's this little bit of research. We saw some things that experts do. What are we going to do? And we want to know anything that's going to affect the ability to solve a problem. And so addition, connect steps and pieces, wants to succeed on the test. Here's some more examples. Wants to succeed on the test doesn't seem like a problem-solving skill. But if you don't want to do it, are you going to do it? Probably not. You've got to have some kind of motivation to do it. So we included anything that will affect your ability to solve the problem, including motivation. Okay, so how can a physics-free measurement be made? So I told you all the reasons why physics gets in the way. So how can we measure these skills you use in physics without physics? Seems not very simple. So what we decided to do is we wanted to study a wide range of people with a wide range of abilities, not just experts. Because it turns out that when somebody can't do something, it's actually a little bit easier to see where they're struggling. When somebody can do something, they just do it. It's like magic and you don't even know they did it. So we found it easier to watch people struggle to identify the skills. So that's what we did. Specific failures show specific subskills. So here's what we chose. So we have this problem-solving skill spectra analysis. That's our new snazzy name, so you'll have to tell me what you think about it afterwards. So we took a problem from the Jasper-Woodbury series. So in the 90s, there was this research and technology group at Vanderbilt that had some really strong people that were there together. Now they're all at separate universities. and doing amazing things, but they were all together and they did some nice work, and they were actually developing these math problems for 6th grade students. But the problems are so in-depth and so complicated that I've given this to physics PhDs and they don't come up with the ideal solution. They come up with a good solution, but it's not ideal. So it makes a really nice problem to use. But at the same time, when I pulled this problem out, my son was, I think he was in 2nd grade, and he was able to come up with somewhat of a solution, something semi-reasonable. So it's great because it works for a wide range of people. So the story opens with Larry, who's this gentleman in the suspenders, and he's teaching Emily. Notice the pictures are a little bit dated, that's the only drawback, but you know, they've been around. He's teaching Emily how to fly his ultralight plane. Then Jasper tells Emily and Larry, so Jasper is the main character. Jasper, they're having lunch one day, and Jasper tells Larry and Emily about this trip he's going to take, and he's going to go into the mountains, and he's going to end up 5 miles off of any vehicle access road. And that's where he's going to go for this fishing trip. And while Jasper's on this trip, a couple days later, he finds a wounded eagle. And so he wants to get this eagle back for medical attention, and him hiking out with the eagle would just aggravate the wound, and it's been shot. It would not be a good thing. So Emily, he radios Emily on his short radio, and he says, you know, you need to help get this eagle out. So she has this complicated problem of trying to get the eagle back, which of course involves this ultralight plane and all the details about what the plane can handle payload-wise and so on. So the solver then is required to help Emily plan the rescue for this eagle. So that's the scenario. And so what I did is I found that when I used this problem, who knows what direction the person would go? How am I going to measure the skills they're using if everybody is taking a different approach? And so I ended up scripting these 2 interns around the problem. And the interns are solving the problem as the person you're trying to measure, the solver, as they try to solve it. So let me show you what it looks like. So this is a sample page. And so we've got Jasmine and Sarah. They're our interns. And the student's job, the person solving this, is they have to decide which of these gals they're going to hire for a permanent position. They were summer interns, and they both did a great job, but the better problem solver is who your boss wants you to hire. And so you have to evaluate their skills. And so that's work to engage the students in the scenario, and it's really helped. So it's a written instrument. As a written instrument, it takes about an hour. In an interview, it takes a little bit longer. And it's a problem regardless of your content expertise. They call it embedded data design, which means you don't need to have content knowledge to solve the problem. Everything you need is within the problem. And it identifies your fingerprint or your spectrum of subskills that you have, strengths as well as weaknesses. So questions have been placed at crucial points, and the person is asked their opinion of how the interns are doing. And that keeps them engaged in what's going on and gives them a chance to say, you know, I would do something different. And they need to be able to answer questions about factual knowledge, planning, procedures, calculations, reflect on the analysis of the 2 interns. So there's a whole range of things you ask these people to do, and you can measure their skills in those things. So for example, you can see Jasmine says, do you think that means we have to count the gas in the tanks as part of the payload? Or maybe it counts extra fuel that you take along. Sarah considers this for a while. That seems strange, but he did say the payload includes fuel, so I think we should count that. What does a full tank of gas weigh? And Jasmine says, how should I know? It held 5 gallons. Does that help? Well, it turns out in the story there was a picture of the gas tank, and right on it it said that it weighed 30 pounds. And so some people have seen that, some people haven't. This gives the solver a chance to say what they know, or maybe they might estimate that it weighs a little bit less than water, for example, something like that. On the next page, the interns introduce the idea of the density, and then one of the notices that's stamped on the gas tank. So you can find out from the person solving the problem if they've caught on to this or if they have ideas. But then, so that the problem can still proceed, a couple pages later, you give them what they need. And so then now, okay, we're past that hurdle, now we can move on to the next thing. Because you know often when somebody's solving a complicated problem, if they get stuck in one place, they're stuck. So this way things keep moving and proceed along, but you can still measure what the person knew as they went. So this unravels the subskills from the whole, reveals their entire spectrum of skills. So far I've completed 30 individual interviews with students and then graded 14 of them where they completed a paper and pencil. And I've come up with a list of 44 subskills that you need to solve this in-depth problem about the eagle. which seems like a lot. I hardly expected it to be so many, but there are individual specific skills that you can need or don't need to solve it. So we've categorized these into 3 categories. So it might be knowledge, things that you know when you come in, and then if you go to the far right, there are processes, things that you do as you're solving a problem. But then in the middle, I'll talk about those after I give you some examples of the others. So knowledge you might have. Well, you have to be able to add and subtract to solve this problem. You need some very basic algebra to calculate the gas mileage of the plane. Students needed to have some number sense. You see a speed limit sign on the side of the road, it goes 60 miles an hour. The ultralight plane goes 30 miles an hour. This is important information if you're trying to save this eagle in a timely fashion. And a lot of people just, to them, planes go fast. It's 30 miles an hour, but planes go fast. So they use the idea that the plane was faster than a car, even though if you look at the numbers. But the numbers to some people just didn't mean anything. They just didn't resonate. Knowledge of own strengths and weaknesses. So we have a bunch of questions at the end that help me measure those things. Things that you do during it. Well, you need to plan what you're trying to find out. There's all sorts of other planning too. How are you going to find it out? But I just listed a couple examples here. You need to be able to connect your steps and pieces. How often do you have students figure out something in part A, and in part B, they don't even know they have that something? They don't connect things. Meta-processing, that's stepping back and thinking about your own thinking. Why am I doing this? How is this helping me? So now, you have these things you do, and you have this knowledge you bring. So what's the category in the middle? The category in the middle is whether you think you need to do those things, and whether you want to. So do you want to solve the problem? Well, I put that under beliefs, expectations, and motivation. Are you careful and thorough? Maybe you have the knowledge, and maybe you're good at the processing, but if you're not careful and if you're not thorough, you could screw up. You could lose something, you could lose track of something, or you could miss part of the question. So there's a whole range of things down the middle there. Some students were very good at estimating, but they just never thought to try estimating. So as a separate thing, do you think it's valuable to do this here? Okay, so is it valid? How do I know that this tells us anything about how students solve science problems? They're solving a problem to save an eagle, talking about ultralights and payload and doing basic algebra. How do I know this is telling us anything about physics? So what we did is, to start with, we talked to physics instructors, and we said, analyze a couple of students, tell us what they're good at and what they're bad at, and then I interviewed those students, and I analyzed them, and then we compared notes. And it looked good. It looked like we were seeing the same thing. So that was enough to say, okay, let's move forward with this, because that wasn't clean enough to be a study by itself. So, and we found that the evaluation matched, and that the PSSA gave us more information than the teacher had from observing the student for a whole semester. So that was nice. So what we did is we took this mechanics problem that was developed at the University of Maryland. It's a very involved problem about the Pyramid of Giza. And we gave 5 students the PSSA paper and pencil. And then I interviewed 5 students solving this problem. And the rule was that they could ask me anything they wanted to, and I would answer any kind of question about content knowledge. Maybe they forgot what the equation is for work, or maybe they needed to know what the equation was for potential energy, something like that. I would give it to them. But if they asked me, how am I going to get this, or what do I do next? I'd say, I can't help you. That's part of the procedure, I can't help you. But if you want content knowledge, I can help you. If you want a calculator, I'll give you a calculator. If you have trouble with your algebra, I'll help you with that. But if you want to know what to do next, or how you're going to go about this, I can't help you. So the question is, given the height of the pyramid, the dimensions of one block, the horsepower that can be delivered by one man over a period of 8 hours regularly, and the time allotted to build, something like 20 summers or something, you're supposed to decide how many men were required to build the Great Pyramid of Giza. So that's the question. So it's pretty involved, as you noticed. So this took 2 1-hour interviews. One student had to come back for a third 1-hour interview. I noticed after an hour, they were just shocked. There was just no more productive thinking. We had to call it, said, okay, I'll see you next week. They came back, they worked again. And when they got to the point where they said they were absolutely done, then I stepped back with them and said, let's read the question and make sure, because nobody actually was done. They had missed part of the question. And so I did have to intervene in that way to get them to keep going and get to the end. So that's how I did those. And then a month later, I graded the paper and pencil stuff. So it was a while later, I'd kind of forgotten about them. Obviously, it'd be better if somebody else had done it, but for this one, this study, this is how we did it. And all the students were easily identified and matched up. So if I looked at their evaluation on the PSSA and I compared it to the skills that they produced, and this is without their names were not attached, they had been removed before I ever graded it, it was extremely clear immediately that, you know, let's say Joe, I'm making up names, let's say Joe was poor at this, this, and this. Well, sure enough, he was poor at that over here with the pyramid problem. And so they all matched exactly like that. And so here's an example. This is, I gave her a pseudonym, Karen is what I named this gal. This is, in the interview, these were the skills that I measured. Notice there's some missing ones, number 7, 10, 22, because I just never was able to see evidence of her using it or not using it in the interview, so I don't score it if that happens. And so this is on a 0 to 3 point scale. 1 means that, and I guess one of these could be that she was so terrible I gave her a 0, but usually you get a 1, means you're really weak at it. A 2 meant that you used it but not great, and a 3, you did a really nice job with that. And so this is what it looked like for the pyramid interview, and then if I put the paper and pencil results next to it, they match up pretty well. You know, there's a few cases where they're not. You can see I was able to measure 7, 10, and 22 on the paper and pencil, even though I wasn't able to measure it for the pyramid interview. So they look pretty good, and so you can see the general trend is there, so I was able to tell who's who. So I was pretty pleased. So this is doing a completely different problem, and they match. So what we did next is we said, oh, I'm sorry, there were some skills that we could measure with the PSSA that didn't show up at all with the pyramid, and then vice versa. There were skills that were needed for the pyramid that don't show up in the Eagle problem. So in the Eagle problem, previously known facts, adaptability, can you adapt to the new information that Sarah and Jasmine give you, was needed. The ability to analyze the interns, obviously there's no interns or group members involved with the interview with me. Enjoyed analyzing the interns, again. Acquires information the first time through. With the PSSA, you have to read a 4-page thing with all the information about the story. So did you get that the first time, or did you have to go back? That doesn't, you saw the pyramid question. It was just like that. And now, you need a geometry to solve the pyramid problem. Don't have to do that to save the Eagle. And what you should know inhibits effective solving was really interesting, because in the pyramid problem, often students were like, I think that there's an equation to find this, which there's not. It was something really goofy spatially they wanted. And it kept them from moving forward, because they kept trying to recall something that they didn't have. And that never happens in the Eagle problem. So that was something that came up that I had to list. Okay, so what we did next was much more rigorous. And we looked at quantum mechanics problem solving. And we compared the PSSA results. And so again, 5 students. What we did is there was an interviewer at CU who had been interviewing students who were in a quantum mechanics course. And she had been interviewing them every other week. She actually interviewed 6 of them. 1 of them never would talk to me. And so she interviewed them every other week about the course and about quantum mechanics and about the PhET simulations. There's quantum mechanics PhET simulations. And she'd already done this. And then we went to her and we said, if I give you my rubric of 44 skills, except at that time I think there were 38, if I give you my rubric, will you score your students' problem-solving ability on this rubric? So she went back through the videotapes and she scored her students. And then I contacted her students and said, hey, will you come in and interview with me and do this Eagle problem-solving thing? And so I got 5 of them, and it took between 4 months and a year to get them to come in. So they had more courses, things had gone on in schools and between quantum mechanics and when I talked to them. And so I interviewed them 6 months to a year, it's like 4 months. And so here's what her interviews looked like. Let's say she used this particular PhET sim, and she would ask them, suppose you're shooting photons at a screen one at a time, and you see a dot appear on the screen as in the picture to the right. Where is the photon the instant before it hit the screen? So that's the kind of questions she would ask. Sometimes they would solve actual numerical problems. So here's an example. So this is one gal, we called her Cece, that's not her real name. And the quantum mechanics interviewer described her in this way. She said she seemed to view learning as how to accept every weird thing we told her. She thought the first step was to accept things, and the second step was to try and understand them. She always rethought her ideas when another student suggested something, although she maintained enough skepticism to recognize that other students were often wrong. So that was her general description of Cece's approach to things. And then if you looked at the general description that I came up, and of course we did this independently and then compared them, it's amazing how similar it is. I said she always had a knee-jerk response, which was not always good, but then on her own, she considers carefully and comes up with the right answer. She'll consider whatever's thrown out there. Decisions are based on the most logical answer. If a suggestion does not make sense after careful consideration, she holds on to her beliefs. She's very reliable. So our general descriptions of her were just really the same, and this is without us having seen each other's descriptions of anybody ever. But then I had analyzed the data the same way you already saw. So this particular person, we named him Guy. And so there were 31 skills again that the quantum mechanics interviewers were able to measure. And so this is the PSSA. So this is the Eagle problem. And so there were 2 skills I wasn't able to identify for him during the interview. And so you can see, and this is on a 5-point scale. Because during the interview, I can do a 5-point scale. Written paper and pencil is much harder. So that's why we only have a 3-point scale for that. So we had a 5-point scale for the interviews, and Sam, who was the postdoc who did the quantum mechanics, also was able to use the 5-point scale reliably. And it took 3 days of training for her to be able to use it. It wasn't simple and automatic. And so here's what it looked like when you compare his quantum mechanics scores. And so they're really tightly correlated. We were really pleased, and they all came out looking like this. So if I show you, I think my next slide, this is all 5 students together. And so the blue is the Eagle problem, and the red is quantum mechanics. And in those skills, they match up almost exactly. And so we ended up with, if the score is within 1, 88.5% of the scores, so 31 scores over 5 students, 81.5% of the scores agreed within 1, and 98.4% agreed within 2. So we felt like that was, considering we weren't using the same instrument to measure them, just the set of skills, we were pretty happy with that. So we feel very comfortable saying that the skills you use doing something generic, like this problem-solved Eagle problem, are the same skills you use in physics. So we felt like we were measuring something valuable that we need in the classroom. This one's interesting because you notice this one is quite a bit different between the two. And that's because I told you with the Eagle problem, it's 4 pages you have to read. So there's a lot to acquire the first time through, whereas in the quantum mechanics interviews, she's asking you a question. It wasn't very often that the person would miss something. Okay, so and then if I compare the skills, there were several skills in the Eagle problem that you need. We did not try to list all the skills in quantum mechanics that you need that weren't in the Eagle problem. She didn't attempt to list every, eigenstates and all, et cetera, that you would need for quantum mechanics. So we didn't have a list for that. Okay, so this is showing you that there's a very different spectra of subskills for each student. So if we look at Rick, he was the weakest of the quantum mechanics students. And if we look at Guy, he was one of the stronger ones. And you can see there's very much a difference between the two of them. And Rick barely made it through that class. I asked Sam, I said, how did he even pass this class? Because when I interviewed him, it was clear he was very weak in a lot of areas. And she said, brute force, just purely brute force. He really didn't understand a lot of things. He just did the work, and he did those interviews because he wanted help. He did anything he could, and he barely snuck by with the C-, I think. So you can see it definitely tells you something about different students. So I thought it would be interesting to look at the physics majors and engineering majors and compare them to pre-service elementary teachers, people who had very limited science background. And so it was interesting because there's some places where the elementary teachers were stronger than the physicists, the physics students, but the physics students were stronger in the areas you would expect them to be. So the physics students were stronger in math, forming equations, their number sense, planning, creativity. So I didn't even notice that until I started doing the numbers and looking for where they were different. And the physics students were much stronger in the creativity category than the pre-service elementary teachers were. And then judgment of reasonable issues. And so those scores in the parentheses are their score out of 5 on average for all the physics and engineering students that I interviewed. And then what were they weak at? Well, the physics and engineering students seem to have weaker metacognitive skills. They didn't use metaprocessing nearly as much. And they weren't very careful and thorough in comparison. I mean, a 2.5 still means they're using it, but they really weren't extra careful and thorough. Now the pre-service elementary teachers, their metacognitive skills were excellent. They knew what they were weak at and they knew what they were strong at, pretty much consistently across the board. They were quite good at that. They were much more depending on the student, but did you have a question?
The metacognition is 4, wouldn't that be high?
Compared to the 5 that the pre-service elementary teachers have. So I'm just doing it as a comparison. Yeah, I should have said that. So not every score, so a 4 in one category is not, just because it's not as likely to get a 4 in every single category, because in some categories you just don't see them using it very much. Creativity, for example, is having a 3.8, that's really high. Whereas in the metacognitive skills, most people do know if they are generally weak at math or they are generally good at, I don't know, what some of the things where they had to do. You usually have somewhat of a sense, and some people are not as good as others, but I never had anybody who was just really terrible at that. Really terrible at knowing they were good at this and bad at this. So that's why those generally end up being higher. But the meta processing, for example, a 3.8 on that is really high, because not very many people I interviewed actually did stop and sit back and say, is this useful, is this productive? And one thing Carl has said is when he would get graduate students in physics, they come in and their ability to step back and analyze what they're doing and whether it's useful is really poor when they first come in as graduate students, and they really struggle, and within a year or two they're usually pretty good at that. So that seems to be something that physics students don't need to use because their skill set is so strong in so many other areas. And the pre-service elementary teachers were actually using it on these basic problems because they were actually quite weak in a lot of other areas. And so it seems to be something you develop when you need it because you're pressed, is what I've seen. So, and then the creativity was very weak for the pre-service elementary teachers. And then other than that, I couldn't say that there was one consistent thing that I saw as a weakness in that population, but there would be something crucial that was extremely weak, and it was different for each person, for each gal. I can say that because I haven't had a guy in my pre-service elementary teacher classes for about 4 years now. So the different things that they're weak at. There was one gal who couldn't plan anything. She couldn't come up with a single, she literally sat, I timed it, she sat for 20 minutes, starting and stopping sentences, never completed a sentence, start to write and stop. She couldn't figure out where to start with the Eagle problem. She just couldn't. And so I said, move to the next page. Just see what the interns do. And as soon as she did, she was good. She could solve anything they suggested. Her math skills were good, her number sense was good, her ability to find the answer. She knew what the problem had said, she knew what things were, she didn't have to go back and look. It was amazing. It was amazing. And she's in a major where it's all group work, and she was a superstar. She had a 4.0, I looked her up afterwards. But she couldn't plan anything to save her life, and it was serious. That's a serious problem. I mean, she's gonna go be an independent teacher, and she couldn't do that. So it was interesting, and that was something she hadn't been asked to do, I guess, in her major. But anyway, so there'd be different things like that. A couple of them had actually pretty poor reading comprehension. They just weren't getting they had a different story in their mind after reading it than what it said. Or they didn't acquire the information first time through. So there was something different with each one, and I certainly wouldn't say that they all had weak math. I would say the majority of them had pretty good math skills. So someone might say, oh, elementary teachers have weak math. You know, they may not have been very confident about it, but their math skills were just fine. So it was something different, though, that each one of them had as a weakness. They definitely had a serious weakness, each one of them. All right, so what does this tell us? You know, does this help us figure out what we're going to do in the classroom? So if you think about the typical problems we give students, typical problems require you to have content knowledge. We do a really good job with that. We know how to give them a whole range of problems where they practice the problems we're giving them, the new skills we're giving them. You have to remember what you've calculated the first time through, because you need to use it for part B and for part C. So we do that. You need to want to solve the problem. It may be for the grade, but that's okay. They do it. You know, students do go do their homework, hopefully. But we don't ask them to practice this needing to acquire information the first time through, because you give them the problem and they can read it as many times as they want to. You know, they don't have to practice being careful that first time. So we don't really give them any practice on this. But it's really important in real life. It's important in almost any job you have that you get this, especially if you're a researcher or involved in something that's timely. You need to be able to pick it up the first time. You can't just go back and reread it, the problem, or re-watch the scenario, or re-interact with this person. You had to do it the first time. Visualizing the problem, we may ask them to draw a picture, but that's completely meaningless if it's not required, if you don't actually have to do it to solve the problem. Just because you tell them to draw a picture, but if they can solve it without it, why would they visualize it? So anyway, you could do this with all of the skills there. You could decide if they're in the classroom or not, but there's a lot of them we don't even give them practice with. So just to kind of sum up, we've itemized 44 different skills, processes, and beliefs that students need to solve problems. We've shown that the same skill set is being used in a whole range of problems. So if you're a good problem solver in physics, you're a good problem solver in history. So we compared trip planning to physics problems in general, a mechanics problem, a quantum mechanics problem. And so now we have this spectra analysis. We just need to make it now so that it's easy to use in the classroom. An hour-and-a-half interview is not exactly easy to use. And so if you want to see a complete list of skills, they're there. They're just on my webpage. And that's it. So, does anyone have any questions? Yes?
I do have one question. You had that slide where you have your course, your subskills divided up into 3 categories, correct? I just want to make sure I have this right. What they have, like content knowledge, right? There's knowledge. Then what they can do. Is that what you meant?
Mm-hmm.
Okay. Then beliefs and motivation are in between, right?
Yeah.
But I guess I'm curious, when I was thinking about this just kind of turned the light on for me. Most of my students have basic knowledge and they can do a lot of the things on the right, but where a lot of them struggle is the beliefs and motivation. I'm just curious, in your teaching experience or anything like that, to me, especially I see this in teenage boys in high school level, they have the knowledge and they can do the things, but they're like, why the hell am I here? They don't have the motivation.
Right.
So is it maybe they're not good problem solving? Maybe it's not that they're not good at problem solving. It's just, why am I doing this anyway?
Yeah.
Have you explored any of that avenue in your research?
I mean, somewhat. So, if something is a balanced challenge, so if it's a challenge, it's not too easy, but if it's not too hard, a person is naturally going to be more interested in solving that. And so that's why video games work so well. That's what they do so well with video games. They figure out how to make it hard enough that you want to do it, but then you have little successes. And you're like, I did it. And it just naturally feels so good. It's better than anything you can give somebody, is their feeling of, I did this. And then that's what gets you engaged in a video game and gets you hooked, and you do it for hours and hours and hours, and you have these little successes, and you build up, and then there's these challenges, and you can do it. And if a video game is too hard, do you play it? No, you quit. You're like, screw that. So I think that's a big thing. Trying to connect it to their real life, trying to have examples and content that they care about. That's helpful.
So that's what you've gone, to me, that's what you want to look for in a teacher, that they can have this bridge between the do and the have. Is that kind of what you do when you're observing other teachers, when you're looking?
Well, I look at a lot of things that they do, but yeah, that's definitely important, that they care about that. If the teacher cares about their students, that goes a long ways too for classroom management and so on. But the thing that it's just like we saw here, 44 skills for that little eagle problem. Being a teacher, I don't even know how many skills are involved in being a good teacher. There are so many things. So, I try to watch for some big ones, but they need to have fairly correct content. That's kind of important, but that's not the only thing. They need to know good pedagogical skills. They need to know how to get the students interacting. And that's the thing, if you can get something interactive for them to do, something hands-on and something challenging, you can usually pull most people in, even some of those really painted about kids. In our schools, we have some that are members of gangs where it's important and required of them to never engage in school. If anybody sees them trying, they're in big trouble. They can't do that. And I don't have any solution to that. But that's 1 out of 50 guys. But still, I think when you get something that's hands-on and it's a challenge and they can succeed at it, like I've done that with my intro labs. We do fun things with spinning buckets of water. Anything that's a good demo for you to show that you have fun showing, put it in their hands. And I find they love it. They jump all over that. It's not very exciting to watch somebody else do it. It's way more fun to do it yourself and to screw up and to get wet or to break this or to break that or whatever. We use elasticity with plastic spoons, and they pull them too hard or they tighten it too hard and the thing snaps. That's pretty exciting. That makes it more fun. So then we're have to do it. Yeah?
Two things. One, an observation. When you talked about how we don't assess them as can they get stuff the first time. My wife, who's secondary at science teacher, she noticed that students were having trouble with listening skills in part because it was a habit to repeat themselves, and she's read about it in something, and it's like, just don't repeat yourself, and then students will learn to listen better.
Yeah, absolutely.
And then the question that I might have is, as far as the grade goes, what should, say, a physics class really be grading on? Should we be grading on the problem-solving skills, or should we be grading on the content knowledge? Because we're making this public declaration to the world, here's the student, here's their grade, as to what they know in physics. Is that supposed to be reflective of the content, or is it supposed to be reflective of the processes?
Yeah, well, the way I do my class is I have my learning goals. I write down, it was kind of a pain in the butt, but I got them put together. I wrote down exactly what I wanted them to be learning, and that's what I grade them on. This is what I want them to learn. I tell them this is what I want them to learn. Then I try to make sure all my lessons are directed at my learning goals, and then my assessment is directed at my learning goals. So if one of your learning goals is that they're going to become better problem solvers, then you say that right up front. You make sure that you give them things that are going to help them to become better. Practice in the different areas. Maybe it's, listening the first time. And then you measure, you grade them on those things. I guess that's what I would say. You might have a class where you're just trying to deliver content knowledge, and you know that, and you accept that, and that's your learning goal. So then you grade them on that. I don't know, hopefully that answers your question. It doesn't just kind of sidestep it, but I wouldn't try to claim that there's one way that we're all supposed to be doing it. I think it depends on the class and your goals for the class. Yeah.
Have you done some work on, especially, I'm thinking especially of the processes, where you clearly identify, that some students have weaknesses in those areas. So how do you teach those?
Well, I haven't tackled that one. Some of the others, sure, I've done things to try to give them more practice, but I think it's all about practice, right? It's about effortful practice. So if you can give them something where they have to use that skill, but you give it to them in a way that they have a chance of succeeding, and you just keep giving them different problems, and you make it clear to them, I expect you to get better at this thing, and I'm going to give you ways to practice it. So that gal I explained to you who couldn't do any kind of planning, when I look back at her courses, it was never required of her. Nobody ever gave her practice, and nobody ever told her she had to be able to do that. So,
but other than just trial and error, it seems like if we're teachers, it seems like there ought to be some way that we can direct their trial and error, so that they specifically get better at that, other than just saying, do more of this, and you'll get better.
Well, it's like with any activity. You've got to, you have to develop materials that are going to work, and there aren't materials that I'm aware of that are developed to help with that particular skill. That's right. Yeah, there are so many things that need to be done once you see what all these are. But yeah, I don't have an answer for that.
Can I see your site again, please?
Which one?
Your site, you have at the end.
Oh, at the end, sure.
Yeah.
Sorry, I have too much animation. Oops. Oh, good. Not very well. Goodness. There you go. All right. Anyone else have a question? Yeah.
So you didn't look at, can they change some of these? You said your quantum mechanics students get it up to a year later, and they're pretty much the same.
They were pretty much the same. Yeah.
So is it that some of these are just part of the way some of his brains work, and they might not be able to get a whole lot better at that?
So Carl and I've had a lot of discussions about these, and he's under the strong belief that absolutely anything can be taught. And sometimes we argue about whether there's innate abilities versus not. And I'm a little bit on there's some innate side to things, and he's on that there is no innate of anything, and I think he's crazy. But but I think that everything can be taught, and with practice, people can get better at anything. And so one example is the metaprocessing skills. these physics majors, they don't really need to use that because they've got really good math skills and they're really good planning and et cetera, et cetera. They're good at those things, and that's one reason they're successful physics majors. Then they get into the lab in graduate school and they're like, holy crap, this question isn't even clearly laid out. But they get better at it. Carl used that as his example of, he's had lots and lots of graduate students, and he said that they all, by the end, are really good at meta processing because they just hadn't been challenged with that, they hadn't been given a place to practice that, and then he gave them the structuring and the scaffolding they needed to learn how to use it. So I think you can learn just about anything unless you have a cognitive disability, but I think you should be able to learn just about anything, and some people it might take a little more practice than others. But if you don't like it, if you don't care about it, am I going to get my pre-service elementary teachers to change their major and become physics majors? No, I'm not. I can try all day long. They, for some reason, have decided that that's not for them. So that, I don't know how you're going to change. Yeah.
For all of Tatum, just as an example, the American does point out that some people are a little bit more intuitive and some people are much more sensory. They're more likely to spell out, and while others will make intuitive leaps. Did you come into any difficulty with assessing, because what's going on internally isn't always going to be reflected?
Yeah, so that's why sometimes there were skills that I couldn't measure. So especially with somebody who's really good at it. So when I would measure somebody who was really good at a certain subset of skills, sometimes I couldn't even give it a value, and I suspected it was because they were so good they were just doing it internally. Yeah, but I couldn't. How can I give it a number if I'm not quite sure they used it? So I tried to scaffold the thing as much as possible to really isolate individual skills, but there are definitely times when people were so good at something, they just jumped to it. I wish I knew what happened inside that got them there, and they couldn't articulate it to me, they just did it. And I noticed the same kind of thing with creativity. If you have to have creativity, you have to have this base of knowledge. It has to be there, and then you can make a connection that maybe wouldn't be obvious to somebody else. But it's because you came with more tools into that. But yeah, definitely there were still invisible things. Anyone else have any questions or thoughts or criticisms? What do you think of the name? We're still struggling with the name a little bit, so we're still passing it back and forth. I was talking to some people at lunch about that. And so problem-solving skill, spectroanalysis, because it's sort of a fingerprint that it gives you. And we didn't want them to think it was just going to be giving you one number of somebody's problem-solving skill, because that's what you naturally expect from the way things are done. So what do you guys think? Do you think that's descriptive, or do you think it's giving the wrong idea?
Skill solving.
What's that? I'm all ears.
How much more research do you have to put into this before you really start?
Well, we're writing up the article right now about what we've done so far. Kind of what you saw here is the content of that article. And so we really kind of need to have a name for it, and we're about ready to turn that in. And then after that, we're going to start working on trying to make as many of the questions multiple choice as we can, or some sort of forced answer. And we're going to lose some of the skills that way and some of the fidelity. But if we can even measure a dozen skills, that's more than what's out there now. So, yeah.
I'm just curious, what are you defining as creativity?
Creativity was if they came up with an idea beyond, let's get in the ultralight and fly and get the eagle and come back. So some people were brainstorming. I guess it would be along the line, they were saying, well, you could put the ultralight on a trailer and drive it because the road is 60 miles an hour, and that gets you closer to the trailhead, and then you could fly in, and then you could fly back, and then a person in a car could drive back. And if you could trailer the plane really quickly, I don't know if you could, and if you happen to have a trailer handy, and people come up with some crazy stuff. So if somebody was going down any of those lines, trying to do something outside the box at all, I gave them the score for creativity. And so some people just didn't, and they had the opportunity. There were multiple questions throughout. They said, okay, would you go a different direction with this? Or at the end, I said, okay, here's the fastest time I've seen anybody come up with. Do you have any idea how they could have done that? And some people would just, they would think and they'd say, I have no idea. This is the only way it can be done. So if they could come up with any multiple solution paths or any ideas, I gave them points for creativity.
Do you have a way to measure their ability to connect just different ideas?
I had the category called Connect Steps and Pieces. So if they took information and they figured out how to connect that to the next part, then I consider that part of the connect steps and pieces. A lot of people were really weak at that, and they did get stuck until the interns did it for them. So yeah, that definitely played a role in there. And there was something that was related but different where if the interns offered some information and they were able to integrate that into the solution, or if they just plain ignored it, I consider that integrating adaptability, being able to go down that new route. Yeah.
Will your article contain any of the qualitative things that the people said when they were doing this? Because that would be really cool to see.
We have this one example here, and that, I don't know, right now the draft doesn't have that in there, but that's nice to hear that that would be interesting to see, because we have a lot of that data. It's all videotaped, we have it all.
Yeah.
It's just, okay, that's useful, yeah.
All the people that were in your study, they were all like about 21, 22?
No,
Or were they older? Or?
No, there were people ranging from, there were a couple of kids, but I don't have IRB for them, so they didn't get listed in the 30. But I did do it with a couple of kids, just for my own information, and then it went all the way up to 65-year-olds. I had 2 people in their 60s. I had a gentleman who has a dropout of high school and he's a business owner. I interviewed him. I tried, and so they weren't all students. I kept saying students, but probably 2/3 of them were students, and 1/3 of them were not, because I wanted a range.
I was just kind of thinking of my own mind, like after getting out of college and then going back and getting into teaching, I really started to like make connections to things when I was about 24, 25.
Mm-hmm.
So I wonder if that would have any, if you followed those people, like if there would be any difference in their ability to solve problems just based
Well,
on
it'd sure be nice to see some
their
growth.
brain growth.
Yeah, because the only range I had were people for that year, and there wasn't any growth. And I've seen growth in my son, for example, just observing him. I mean, I know there's growth. It'd be nice to see where there's so many things you can do with this, and you can get it so it's easier to use. So then you could look at some of those things. And when I think about it, there was probably 7 people over 25 that was in my group. So there were some there. And some of them were pretty weak, and some of them were really good. So it looks like Kevin's chomping at the bit to move us into the next phase, so.
Let's thank our speakers.